Hello, everyone, and welcome to Teachings and Education. Today's presentation will be on a very interesting topic, problem solving education. This entire presentation, and let me open this up full screen here. The entire presentation is going to teach different strategies for students, and not just students, also us as educators, different strategies for solving problems. And it's not just solving problems in an assignment or test taking way, but just solving problems in general. And our career readiness standards that we find in different states usually focus on the ability to solve problems. And I know, even if you look at math problems, and excuse me, if you look at math standards, many of them mention solving problems. So the ability to solve problems is ingrained in education. So I think this is an important one here. And there's a lot of interesting stuff that goes on here. So let's get to it here. So usually I have an opening video here that you can take a look here. It covers all the different stuff that we're going to do. This is a brief big picture video, kind of everything that we're going to go over. And I use some of these images for part of the presentation. But this presentation is going to be an in-depth presentation, so we get a full understanding of problem solving here. So I'm going to skip this. I'll provide a link above if you want to watch the video. So let's get into it. A problem solving is using knowledge and skills to find solutions to real life problems and finding answers to difficult questions. So solutions and finding answers to questions. And we're going to go over a couple different topics here. We're talking about goals, givens, operation. Let's get right into it here. So again, right, so it's using knowledge and skills to find solutions to real life problems. Problem solving gives us a method for understanding what is currently wrong, figuring out how things are broken, and then devising a plan to fix life problems. Now, take a look at this Rubik's Cube here. When I worked in Washington Academy, there was this math teacher, and he used to do the Rubik's Cube. He would bring it in, and the students would get it wrong. And I remember when I first saw him do it, I was so amazed. And still, it's an incredible feat, right? And by the end of the year, he'd be able to teach his students how to do this Rubik's cubes. And he explained that the middle piece doesn't move, and basically, if this middle piece is yellow, then that means this is the yellow box. You know what I mean? And if this one is blue, then this is the. And from there, he would teach them like a little algorithm and little tricks and things like that. And this problem, the Rubik's Cube, which I thought was so impossible to solve, he did it. Good math teacher, and he was able to teach his students how to do that. So, keep that in mind here. That however difficult we think a problem might be, there's a way out of it. So there are generally two types of problem classifications. Okay, there are well-defined problems and poorly defined problems. Well-defined problems can be solved. There are solutions to well-defined problems. Poorly defined problems may not be solvable, and there are cases. Not every problem can be solved. So, what do we already know about problems? Well, a typical problem can be solved. A typical problem to be solved sets a goal or objective for the learner. Okay, so again, we're just on the overview of problem solving, right? So there must be something that we have to do. The objective must be met for successful completion of the problem. So problems require given information that the learner must make sense of to achieve that goal or to achieve that objective, right? So if it's a math problem you're given and you're saying something like there's 25 ducks in a pond and 3 ducks swim away, how many ducks are left? The goal is to know how many ducks are left after the other ducks swim, and the information given is what they told us here. So, you start with 25 ducks, right? Now, what do we already know about problems? The learner must decipher useful and necessary information from unnecessary information. And if a problem is written correctly, or a good problem, let's say, it would be one where students have to be able to differentiate what is useful information and what is unnecessary information. So, if we go back to that duck problem, I'm just using this. There's 25 ducks in a pond. It's 78 degrees outside. 3 ducks swim away. How many ducks are left? That 78 degrees is not useful information. We don't need that number. That 78 has nothing to do with the ducks, right? So, I'm just using this as an example. Now, problem solvers often need to use various operations in order to solve a solution. And you can think about math. These operations don't necessarily have to be mathematical in nature. Okay, algorithms and other methods work. So an algorithm is kind of like a strategy. We're going to get to algorithms later on, though. So let's talk about creativity stages. Okay, so Wallace and credit to Wallace talks about 4 stages of creativity, and this relates to solving problems. Okay, you can see a preparation, incubation, inspiration, and verification. So the 4 stages of creativity outlined below are credited to Wallace, and preparation and these are the 4 stages. Now you have to be creative to solve many different problems. Okay, a lot of us think thinking outside the box here. So you can just look at this thing at a box here, right? And let's say it's taped and this and that, right? You have to think to yourself, how do I open the box? Well, you say to yourself, okay, I got to go, I got to get a scissor, I got to take the scissor, got to cut it, open the box. But sometimes maybe, you don't have a scissor, then what are you going to do? You have to think, you have to create something. If I don't have a scissor, what do I do? And you go in your pocket, you have your little keychain, and maybe that will work. So you have to, creativity goes hand in hand with problem solving. So the preparation stage. Learners look to gather as much relevant information and necessary resources as possible, right? You want to know as much about the problem as you can. Problem solvers tap into whatever prior knowledge they possess in order to solve the solution. So if a problem was solved one way before, like how to open a box using a scissor, you can do it again in the same way. The problem must be investigated from all different perspectives. Okay, you want to look at it like you always think here. Look at I think back to Law and Order and things like that, and a lot of times they'll say maybe we got to look at this from a different angle. We got to look at this from a different perspective, and at the end the detective gets that aha moment. Okay, so again, right, they have to be investigated from all different perspectives. Research, pre-planning, and attention are necessary. Okay, again, think back to, like I said, Law and Order. They have to they have to go out and they have to investigate the crime, and they have to pay attention to what things are said. They have to write things down if they're trying to solve a crime or something like that. Sorry. The incubation stage, right? So again, right, it's preparation, preparing. Next is incubation. So here individuals take the time to digest the information until a moment of insight arrives. The incubation stage is essentially a period of unconscious processing. So, that's sort of tapping into your intuition, as they say, like the detective's intuition. During unconscious processing, there should be no specific effort or energy spent on the given problems. Learners, you have to kind of let the mind do its thing. Okay, digest the information. I'm going to the cop show and things like that with investigating. Just because it doesn't come to you like that, that's okay. Again, this is the incubation. You have to give it time to, like we said, let the mind do its thing. It's called unconscious processing. Okay, and then the inspiration, or as he calls it, the illumination stage happens. Okay, in this stage, the learner arrives at a possible solution to answer the problem. If we go back to that box, you want to open the box, it's taped. You don't have a scissor, right? So how are you going to open it? Well, just give your mind a second. All right, so think about, and you say to yourself, you know what? I have the key. The key's kind of sharp. That's the inspiration stage, when that thought pops into your mind. So that possible solution may be correct or it may not be correct. Okay, maybe the key doesn't work. Learners may describe this as a moment where everything just clicks. So here, concepts and ideas are connected and manifest themselves in the correct order. Lastly, the verification stage. excuse me. In this stage, learners must check and verify if the possible solution arrived at from the illumination stage is correct, right? They have to actually go through and solve it. Can the scissor, or excuse me, can the key open the box? Maybe not. Maybe the key's not sharp enough. There is a deliberate and conscious effort at this stage opposed to the illumination and incubation stage. That's just thought here. In the verification stage, you got to put out the work. Many times, the possible solutions that came about don't work. In that case, the preparation stage needs to start and begin again, right? So if the verification stage, excuse me. So if the verification stage doesn't work, you go right back to the beginning and start again. And that's okay. It's a process of learning. So, creativity is a special gift where it makes life more enjoyable by opening the mind to different ideas and perspectives. Okay, we want to foster this in our students, creativity. I recently did a presentation. I believe it was on 21st century life skills. And I was talking about the 4 C's and everything, and creativity was one of them, and how important it is for students that creativity is something that they can take with them to careers and jobs. So, these ideas on the 4 stages of creativity can be found in the Book of Thought, 1926. The Art of Thought, 1926. You want to read that. Okay, metacognition. That's having an awareness and understanding of your own thought process. Okay, you have to understand what's actually going on, the way you think and attack a problem. So, metacognition, generally speaking, is an awareness of understanding your own thought process. It's the simplest and most common way to describe metacognition is just to think about thinking. Okay, say to yourself, am I thinking this? Am I thinking the right way? Am I thinking about how to do this the right way? Am I attacking this problem the right way? And it's an important component of learning. Learners that utilize metacognitive strategies develop a confidence to take on challenging problems. And that confidence leads to an increased number of attempts. The more times you try to solve a problem, the more likely you are to actually get it. Because as we continue to try, that grit, that growth mindset, we're likely to overcome. We're more likely to overcome that challenge. When you understand your own thought process, your metacognition, you're also more equipped to develop plans to take actions and to take on that problem. So, this is, what we want to teach. That's like test taking strategies for students. I know many teachers are against, teaching students test taking strategies. They're like, oh, we shouldn't teach the test, but you're really preparing students, to be successful on future tests, not just your test. Using metacognitive strategies will also help learners to evaluate the plan of action. Just as metacognitive learners evaluate their own plans, they also evaluate themselves as they attempt to solve the issue. Learners using metacognitive strategies are more likely to put in the extra time. Okay? And lastly, metacognition means being able to monitor oneself as you go through the process. Okay, so we're going to look at some strategies here. I have 9 different strategies. Okay? The first strategy is the trial and error strategy for solving problems. Okay, testing possible solutions until the right one is found. Trial and error. We all use it, and let's talk about it. So, Thomas Edison's method, they called it the Edisonian approach, is an example of an individual using the trial and error process. He did not like doing math. So what Edison would do, Edison would try and fail using different experiments until he finally got the right one. The strategy is also called hunt and search. So I think the story goes when Edison was trying to find something that illuminates for the light bulb, and I can't think of what the substance is called, but he had tried like 1,500 other compounds or substances until he got the right one, and he just kept trying and trying, and we're all better off for it. So this is the trial and error. If you look here, there's a picture of a plug, and here's a puzzle thing. You don't know if the piece fits. Just try one piece, or don't try the next piece. Try the next piece. Trial and error is about increasing the number of opportunities in order to achieve a viable outcome. This works best with a small sample size, where learners will have the time to try many different options. So with a big, if you're trying to find the right object that fits into a hole, and there's, I don't know, 25 different sized objects, and you got to find the right one, that's just way too big of a sample size, especially for students. So the smaller the sample size, the better. If you have, I can think about my daughter when she had the little blocks and she had to take the star and put it in the star hole. If there's 4 pieces, a star, a circle, a square, and a rectangle, you try the first one, don't work, try the next one, and then the fourth one works, and that's a small sample size. That's your trial and error. Consider the strategy sometimes used in putting together a jigsaw puzzle. You simply try different pieces. With trial and error, try a method, see if it works, and if it doesn't work, you try a new method. You can also apply this to methods, not just in an object or things like that. Try different methods for solving problems. Trial and error, that's a good one. So the next one is algorithms. Okay, algorithms are step-by-step procedures for solving specific problems. And you can see here combined algorithms, programming, formula, etc., etc. Algorithms are simple step-by-step procedures for solving problems. Algorithms are used for solving well-defined problems. The quadratic formula is actually an example of an algorithm because it is a method to solving a specific type of problem. It's used for solving quadratic equations. You take the A, the B, and the C. When you line it up, set everything equal to 0, you plug it in and you get an answer. It's an algorithm. Formulas may or may not be considered an algorithm. So, I put that there, but it's close enough, right? So formulas almost always involve numbers. For example, the force of gravity. Algorithms, on the other hand, don't always have to involve numbers, but they can be a set of rules or parameters to follow. So they're a little different, but still somewhat similar, right? So an algorithm is just a set of rules to follow to solve a specific type of problem, right? I mentioned earlier it's for well-defined problems. Computer programming is a common place where you would find the repeated use of algorithms. Computer programmers create a set of instructions for an action. Various types of engineers use algorithms in their practice as well. It's quite common in the field of computer programming to find a number of different algorithms being combined to create a larger algorithm with a distinct purpose. Often the biggest issue is finding the right algorithm to use. So the algorithms are out there, but then you have to find the right one. All right, the root cause effect. Identify a factor that is the main cause of the problem. So here we go. Besides the root cause, there's also a number of additional causes, right? So the root cause is the main cause of the problem, but then there are additional causes that aren't actually responsible for the problem. So the root cause sets in motion a cause and effect reaction that ultimately leads to problems. Chelsea Cho says, find and address the root cause rather than try and fix the effect, as there is no end to the latter. So, once you fix the main cause, you should be able to remedy the additional causes. So let's talk about a little bit more about root causes. Learners must differentiate the main cause from additional causes. This is what automobile mechanics are supposed to do, right? So you take your car into the mechanic and, you got the light that says engine. And then you go there and you ask the mechanic, can he fix it? And he tells you got 25 different things wrong. And let's say you pay him. And then, he fixes this, he fixes that, and that light is still on at the end of the day. He didn't fix the root cause of the problem. Okay, whatever the root cause was causing that check engine light to be on. A good mechanic knows what the root cause is. They can look at the car and they can, remedy that problem. When mechanics fix only the additional causes, the car may continue to break down until the root cause is fixed. So, the root cause is the main one. Similar to mechanics, good doctors attack the root cause, not just the symptoms. Root cause analysis focuses on identifying the sequence. Okay, so you want to find specifically specifically where the sequence originates. And that applies to the medical field. A good doctor, okay, should be able to identify the root cause, not just, not just fixing the symptoms. You know, with medicine, I have a good doctor, and he says that he's always talks to me about the root cause and the symptoms and explains it to me. That's hopefully you have the same relationship and the same type of doctor, because I had bad allergies, and I had one. I went to an allergist, and he was constantly just talking about fixing, take this medicine, take that medicine. But then I had one that wanted to actually attack the root cause, which was, the immune system, and he gave me a shot that really kind of fixed my immune system. And then I kind of wasn't having allergies, whereas the allergist, I think he just wanted me just to constantly come and pay money or whatever. But when I got the shot, it really helped out. All right, self-explain. I use this all the time. So that's talking to yourself about the problem, talking out loud sometimes, just thinking about the problem, right? But talking to yourself in a way that you realize what you don't know, what you do know. So self-explaining this is the fourth strategy. And again, right, it involves talking to yourself about the problem, the steps to solve the problem, and what the solved problem looks like. This strategy is tied to critical thinking, the objective analysis and evaluation of the problem at hand. Okay, so when you talk to yourself, you have to really think about it and examine the information and examine your thought process. Very similar to metacognition. How many times have you talked to yourself out of a bad idea? And it's like, oh, should I? It's very late at night. Should I? Should you go out partying late at night? There's many different bad ideas we've talked ourselves out of, and some that I haven't talked myself out of that I should have. So teachers should consider devoting time to helping their students develop critical thinking skills. That's an important one too. There's also a video here on critical thinking in the classroom, but we're going to skip this now. Sorry.
Hello.
Skip this one. All right. When attempting to solve a difficult problem, it's likely that you'll get stuck. At this point, it's recommended to use the self-talk strategy when you don't know how to solve the problem. This strategy allows learners to realize that which they do not know, thus bringing them closer to solving the problem. So when you get stuck, try to talk to yourself. Talk to yourself. How do you solve the problem? Brainstorming. Okay, this is also used as a lesson too, and it's a kind of like a formative assessment here. So we're on brainstorming, the fifth one. So this is the process of collecting large numbers of ideas and solutions until the optimum choice is found. So this activity may occur with an entire classroom or an individual level. Okay, so brainstorming is you're just going to get a whole bunch of, let's throw all these ideas on the wall. Let's write them all on the board. In a whole class brainstorming approach, it's important that there's never any judgment with brainstorming. So there's never a wrong answer when you do brainstorming. This is with yourself or if you're teaching and using brainstorming. You could say, hey, what's an example of a fish? And somebody says a dog. You don't just say, oh no, you go close or whatever, but you don't want to judge anybody. You just want to get the ideas out there. If the dog is wrong, you don't write it on the board, but you just want to get a number of ideas. You want to get as many ideas as possible. And you throw out the crazy ones. When a person is leading a brainstorming session, you want to create a warm and friendly environment. A session should conclude on its own, and usually someone will come up with a mutually agreeable idea, and that is the idea that the group will utilize to solve the problem. So you put a bunch of ideas on the board and you pick one and you go with it. Analogies. Get creative ideas by comparing it to similar problems. Okay. All right. So analogies are described as what's called an abstract parallel between two different things. For example, if you say settling for a field goal in football may be similar to settling in court. So if you're the coach of a football team and you're driving down and you get down to the 15-yard line and you can't get a touchdown, do you go for it on fourth down and try to get the touchdown, or do you settle and just take the guaranteed 3 points instead of risking it for 7 points? That's similar. Maybe in settling a court case where you wanted to get a large sum of money, but you don't know if that's going to be successful in a trial, so you settle on court for a smaller amount. So that's an example of using an analogy. an abstract parallel. And that type of thinking often helps with problems in life. So using analogies as problem solving strategies may occur the transfer of skills, not just ideas. Something learned in one place can be used in another place. If you learned how to, if you're good with working on your hands outdoors, you're probably good with working on your hands indoors, or maybe, as a teacher, you'll be able to craft I don't know, to do some sort of an arts and craft lesson or something like that. So it's also skills. The purpose of college and vocational schools is to learn knowledge and skills that they can transfer to future careers as well, right? So it's a transfer, right? Analogies doesn't have to just be, a mental way to solve a problem. It could also be with skills. So if a learner used a particular way to solve a similar problem in the past, they can draw an analogy between the way they solved the problem in the past with the present problem. The method used in the past may be slightly different, but it could be enough to get an idea. Learners can draw analogies between previously used methods for solving similar problems. Visual imagery. That's making mental visualizations that can facilitate problem solving. So if you can visualize it right, you can do it. I was from a movie, but that line always sticks in my head, right? So this is the seventh strategy we're going to talk about, and mental visualizations have a number of benefits, including the ability to help facilitate problem solving. Visual imagery will aid in memory retrieval, which is often needed as raw data for information. So a visualization may cue the brain to remember relevant and useful information to solve a problem. One of the most common ways to use visual imagery is to draw out a diagram. Okay, so maybe you're trying to think of, the parts of the body, and I say name 15 bones in the body, and you can't really think of them. But then once you start drawing the body out, you go, okay, humerus, okay, a radius, ulna, because you're drawing the body out. Now you're able to visualize that, and you can think of a way. This is another excellent way to solve a problem. So drawing out diagrams gives learners a different look and a perspective that can positively impact the way a problem is solved, right? So remember, earlier in this training, we talked about, solving problems. The detective wants all different perspectives. So, this whole strategy here, visual imagery, is another perspective, right? We said analogies, we said trial and error, all different ways. And drawing a diagram is great for learners with an above average spatial recognition. These individuals are sometimes referred to as having spatial intelligence. An example of spatial intelligence would be a person hiking and having the ability to use a compass, and being able to map correctly how to travel. Okay, backwards thinking, working in reverse, one step at a time to initiation. So we're going to talk about how backwards works. So working backwards means working in reverse, and this is our next strategy for solving problems. One step at a time, right? Working from initiation to verification of the solution. Should be, one second here. Working at one step at a time to initiation. So it should be, eventually we want to get to initiation. And then you have to verify the problem too. So working backwards to initiation and then to verification. So in mathematics, teachers often encourage students to use this strategy for word problems and other types of problems where the solutions aren't readily apparent. So in a lot of times in math word problems, especially trigonometry word problems, I always tell them, try to work backwards. Okay, you know what they're asking for. Then ask yourself, what kind of problems do you know, what kind of steps would you take to get there? So working backwards is comes up a lot in, I think, just schoolwork in mathematics. And a great example would be a maze, okay? So it says here, other examples of times where working backwards is optimal is finishing a maze. If you want to solve a maze and you start from the beginning, you're likely to go the wrong direction. If you work backwards, it's a lot easier. It doesn't always, it's not perfect working backwards, but you're going to be better off. In the business world, backwards thinking is sometimes used as a method for focusing on customer needs. Prominent companies, and these are good stock companies too. I encourage you to invest in these two here, Apple and Microsoft. Um, Apple and other companies have used this problem-solving strategy in their business models. Okay, so they use this backwards thinking approach, and what does the customer need, and then they solve it. Means end. Okay. Okay, so the breaking of a problem down into two or more similar problems, and then working on those problems. Okay, so means end. So you're gonna break down a problem and solve it kind of one at a time. So means end analysis is, like we said, is the breaking down of a larger problem into two smaller problems and then working on those, right? So a means to an end can be described as an action taken with the sole purpose of reaching the desired result. So you look here at the road, like you go left, you go right, you got to do one thing at a time here, and then you get to the end. It focuses on goal-seeking behavior. It includes doing whatever is necessary on getting to the goal. All right, you ever hear the saying, by any means necessary? So you're going to have to knock down this obstacle. You're going to knock down that obstacle, doing it one step at a time, all to get to that goal. Okay, so those were like our 9 strategies here. Now we're going to look at some cognitive factors, which is the ability to solve problems is related to one's own cognition here. Okay, so this is sort of like an overall look at problem solving and cognition. So what is cognition? Cognition can be defined as the mental processes necessary for the acquisition of knowledge, the comprehension of that knowledge, and its application. So the ability to solve problems is directly proportional to an individual's cognition. Cognitive factors, however, affect the learner's ability to solve problems in multiple ways, right? So cognitive factors can increase or decrease over time. So these cognitive factors are going to affect how you solve a problem. So you have some here, but we're going to go into them. So some cognitive factors include, one is confirmation bias. So confirmation bias prevents learners from solving problems, and that learners don't want to challenge their pre-existing views. If you believe the only way to, let's say here, the only way to cook a healthy deep fried meal is to do X, Y, and Z, and you never want to try something else, and you don't allow yourself to use the air fryer, you're being limited by your pre-existing views. Okay, a lot of coaches go through this. They don't want to update with the changes of the game. Teachers specifically don't want to learn technology because it can go against their pre-existing views. So this confirmation bias prevents learners from solving problems. Functional fixedness, that's a cognitive bias that implies learners will only look at things one way and not be able to think outside the box. They're zoomed in on one way. Let's go back to what I said earlier. You have a box and it's taped and you want to use a scissor to cut it open. If you're on functional fixedness and you go, the only way to open this is with a scissor, you're not going to think outside the box and say, oh, I could just use something else. I could just, I'll get this here or whatever. Maybe you just wait around till, or you don't think to use a knife or something like that. That might be a poor example I'm using, but trying to get the point out there, right? So focusing on just one way, you don't think outside the box. Knowledge base. You have to have a pre-existing knowledge that is related to the problem at hand at times. So that may be necessary. So having a pre-existing knowledge may be necessary, and that comes with math, right? So you talk about the ducks in the pond, right? I said 24 ducks, 3 ducks swim away. How many's left? You have to be able to subtract 3 from 24. If you don't have that knowledge, you're not going to be able to do the problem. And memory, the learner must have a strong memory base, as well as the ability to retrieve memory. This comes with a lot of just like a social studies test, and they're asking you a question on, I don't know, one of, the Industrial Revolution, and you have to explain something. So you might need to tap into your memory and whatever, you remember about learning about the Industrial Revolution to solve that problem. So look, here is the overview of everything we did, right? We went over the overview here. We talked about basically what problems are. There's well-defined and poor-defined problems. You got to solve the goal. They're going to give you information, and you're going to use operations. Our cognitive factors that are going to affect our ability is our confirmation bias, a functional fixedness, knowledge base, memory, We also talked problem-solving strategies here, trial and error, algorithms, root causes. These are the 9 strategies I went over. I think there's a few more. And then we talked a little about metacognition, thinking about the way thinking is important. And don't forget the 4 stages of creativity. Okay, we did that earlier too with, you prepare the problem and then, you go through the incubation stage where you kind of just sitting on it, and then you get the illumination stage where you get what you think is the right answer, and then you have to verify it. And so, this is it right now. All right, let me get out of here. I want to say thank you for your time. I appreciate everything. I'll see you at the next training. And if you want to work together with me or something, just write something below.